Hello, community! So great that you are back. Today we talk about gravitational wave artificial intelligence. We're going to tokenize a gravity wave and we will swap the probability functional for a beautiful performance increase. Of course, we're going to talk about a gravitational wave spectrography AI, and if you want, with an inference functional for the LIGO detector. So let's start. Welcome to my channel, Discover AI. We have a look at the latest research paper here in artificial intelligence. And you might say, wait, we just looked at molecular AI for protein folding with an AI swarm multi-agent system. And then we looked here at a medical AI system and what the implementation of a safe protocol really means here in the real world, hospital and environment. And now we swap here to gravitational waves. And you might say, why? The reason is simple. I learn here best from real-world use cases. Real-world use cases that provide some amazing technical insight into the AI technologies that the expert team use in their domain. And astrophysics is something I'm absolutely fascinated, and I hope to show you we have some brand new ideas emerging from astrophysics. Now, gravitational wave detectors like LIGO, they measure here the ripple in our space-time. And this can be real faint patterns that even a truck driving by miles and miles away or thermal pop in the instrument, this is known as a glitch. And it can drown those real gravitational signals completely out. So what we want is, we need an optimization of the, if you want, pattern detection mechanism with AI for the next step of LIGO, and the LISA will be the next step. It will be a laser interferometer, a space antenna that we position in space, and we can have here arms that are more than maybe 1 million kilometers long. So we will have some beautiful interferometric pattern, and we will use here new AI algorithm to detect those faint gravitational waves. And here we are. We have a brand new publication I'll show you in a second, December 3rd, 2025. On top you see here, this is a gravitational wave event. Those are the real signal data that you have to interpret. And at the bottom, you see pure noise data. And the job of the AI is to go and have a probability, an accuracy of above 97% to say, yes, I detected here a real gravity event. Let's have a look how to do this. Now, to analyze those data, those are dominated by non-Gaussian and non-stationary noise patterns. So therefore, any AI model must satisfy two requirements. It must remain robust to localized heavy-tailed noise, and it must be able to extract a coherent pattern that extends across time and frequency. And normally we work with convolutional neural networks, but I will show you they have here a real problem for the feature extraction because they work with a localized convolutional kernel. And this is not good enough anymore. This is here the formula. So, interferometric gravitational wave detectors like LIGO or LISA measure now a high sampling rate strain time series. And of course, you have here with H your astrophysical signal here with all the parameters that you're interested in, and you simply have noise, instrumental noise and noise from so many other sources, and you just want to identify the pure signal. Okay, let's do this. Now, standard mathematics assume that the noise is a stationary Gaussian process, fully characterized by our one-sided power spectral density function, our PSD function. Now, unfortunately, in a real detector world, this is not the case. This will violate our assumption in several important ways. Dominant feature is the presence of a short duration, high amplitude transient artifact known as glitches. These events appear as localized or narrow-banded structure in the time-frequency plane, and they introduce heavy tails in the noise distribution, which is absolutely incompatible with the Gaussian ideas. So therefore, we have to come up with a better mathematical idea. In addition, all the gravitational wave noise is strongly non-stationary. Just think about what could happen on planet Earth. Environmental variations, maybe we have some seismic motion, maybe we have some thermal drifts here if there was a real cold night or whatever, and changes in interferometric control state causes our beautiful PSD to evolve over minutes, over hours, and somehow we cannot control this. So all these effects break here the assumption that a single stationary PSD can describe here long data segments. If you want to read more about this, I have a recommendation. I think this article here, Physics, Astrophysics, and Cosmology with Gravitational Wave here, and this is a publication from 2009, is really excellent. So if you are interested here in gravitational physics, Max Planck Institute for your gravitational physics here, this is really something beautiful. Yeah, we can have a clear idea about the signal we expect here. We have an astrophysical compact binary signal, exhibits some coherent and predictable evolution. The instantaneous frequency of an in-spiral follows here a particular pattern here, a chirp pattern, producing a smooth monotonic chirp track in the time-frequency plane. So we know what we are searching for, but we just have millions and tons and whatever of data. So how to do it? Now, I already told you, we have here classical convolutional neural networks. They have a local bias. They look the data through a small window through their kernels. And when a CNN sees here a loud glitch or intense burst of noise, it often reacts too strongly, thinking, hey, this looks important. Maybe I have found an event that I'm looking for. But unfortunately, it leads to false positives. So therefore, to fix this, scientists had to train here this CNN with hundreds of thousands, and I really mean hundreds of thousands of fake signals to teach this stupid CNN what not to look for, to discriminate a signal from a noise pattern. But we are not really successful. So this new idea is now, okay, we have two black holes spiraling in, so we have a beautiful gravitational wave signal. We can detect this, have now a beautiful digitalization of the signal, and now we just have to convert it to tokens. And now those tokens will be here, if you want, the quantization effect for our artificial intelligence system. So let's do this. And you might say, hey, wait a minute, how can we convert a three-dimensional gravitational wavefront into a linear sequence of tokens? And I just can say, hey, I'm so glad you asked, because this is it. This is the flowchart. We have here our astrophysical signal here. Then we have here a particular transformation I'm going to explain in a minute. We come up with a beautiful spectrum. We can do some patching. We can have a k-mean quantization effect and suddenly regenerate tokens. And it doesn't matter for here the transformer what this token is encoding, because we decode it at the rest. But the LLM knows exactly how to do a pattern matching with 100,000 of tokens. So we use here now the power of an LLM to process our signals. And you know what? The authors of this study had some beautiful idea. They took an old Llama 3, a generic text model, not a vision language model. No, they said we stay purely in linguistic in text. And they fed here a particular gravitational wave spectrogram pattern into this LLM. And after they figured out, after some time, how to do it in the right way, and I'm going to explain this, the result was just startling. While our CNNs needed massive synthetic dataset to learn, with LLM something unbelievable happened. The LLM achieved a state-of-the-art accuracy above 97% using only 90 real-world examples. 90. Compared to 500,000 with CNN. And you see immediately, this is exactly what we have been waiting for. So how we do this? Transformation, the first step is here, the famous Q transform. So they converted the time series into a time frequency representation, what we call a spectrogram, using here the old-fashioned constant Q transform. This aligns with how the astrophysical signals here, our chirps, manifest itself here. They evolve in frequency over time. And this is here a standard formula. If you want to see this, and I went to the library to really find out when did it happen the first time that we used this, I found here 1978 IEEE International Conference on Acoustic, Speech and Signal Processing, and they were the first to talk about this methodology. They said a generalization of a short time Fourier transform is presented, which performs a constant percentage bandwidth analysis of time domain signals. The transform is shown to exhibit a frequency-dependent time and frequency resolution. A synthesis transform is also developed, which provides an analysis synthesis system, which is an identity in the absence of spectral modification. Finally, similarities between the constant Q spectral domain and the human auditory system are explored. Unbelievable. 1978, we found the methodology for this. Yeah, then step 2, patching and quantization. So the spectrogram is simply sliced into time intervals, into time patches. And to make this text-like, they will use here a k-mean clustering function on the feature vectors of those patches. So each patch is assigned here the nearest cluster centroid, and the cluster ID, for example, becomes here the token number. Okay, simple. The result is now, hold on to your socks, a continuous gravitational wave interferometric pattern is now a sequence of integers which Llama 3 can process just like any other human sentence and find a pattern. Amazing. So again, our convolutional neural network had a massive problem here with local processing because we're only looking here at local kernels. The transformer computes a self-attention. You know this, classical. So for each token x sub I, the patch of the spectrogram, it looks now at every other patch x sub j. So this signal, a gravitational wave, follows, as I told you, a smooth curve. Now, with this transformer analysis, the patch x start position strongly correlates with every other patch position up until patch x at end, because they are part of the same physical evolution, of the same chirp, of the same, if you want, sentence, gravitational sentence. So, if you remember here the formula of attention, and I have it here for you, the query, the key, and the value term, softmax function of q times k transposed. Now this q times k transposed is now high for the signal. And we want exactly the opposite to be true for the noise, no? And guess what? This is working. So for the noise, the glitch can be now isolated because the glitch signal does not correlate with the past or future context. Therefore, the mathematical term q times k transposed is low for distant tokens. So we found exactly the discrimination between the signal and the noise. This is what we set out to do. So this global softmax effectively downweighs now the glitch and upweighs here our pure signal because it forms a coherent sentence and it is processed by an LLM. Now, I was just amazed. Look at this. Here we have the confusion matrix. And they fine-tuned now an LLM on the LIGO observational data with only those 90 events. And you know what? If you go with the true label and the predicted label, you can show that if you want the quality, the accuracy is here 97.4% in both cases, which is just amazing for this AI performance, given we only had 90 real observational events to fine-tune this LLM on LIGO data. This is here our main study. Look at this. LLMs for limited noisy data, a gravitational wave identity study. And we are not anymore looking here at publications in AI. I found this in Astrophysics here, of course, but whenever I saw large LLMs or large language models here in Astrophysics, I had a look at it and I found it to be absolutely fascinating. So, thank you to all the authors, to all the institutions here from China, Italy, France, Rome, China, and Italy. What a beautiful study. So the training regime, maybe you're interested how they trained this. They took an old Llama 3 and 8B instruct model and they used here a beautiful technique that we know as a LORA adapter. So they froze all the massive dense weights of the Llama 3 and only trained here a rank decomposition matrix here of this low rank adapter, of a LORA adapter, with only 90 events. And compare this to the classical up until now, where you had a pre-training of 500,000 simulated samples that did not improve the performance. So we really understand we have to move here from a convolutional neural network where we see the signal as an image to a large language model where we have everything how a transformer works. So LLM now learns the fundamental morphology of this chirp signal, of this real gravitational wave interferometric signal from just a few real examples. And this is perfect also then for the space-based LISA implementation. Again, here we have our real astrophysical signal. Then we have our transformation with constant Q transform. We have here our time frequency spectrogram where we have this chirp that we are looking for. We do here a simple patching here. And we have our tokens. Look, and the classical transform architecture doesn't care what is the real content of a token. It just takes integers. So k-means quantization is here the solution. So let's take a step back. Okay, we have a gravitational wave signal, a GW signal. This has a very particular form, shape, and time dependency. So are we really safe? Let's have a look. At the start of this GW signal, we have a low frequency that is evolving slowly. So you need now to have an algorithm like the CQT, high frequency resolution here, to track here the slow climb at the beginning. But at the end, at the merge of these two black holes spiraling together, you have a high frequency evolving instantly within milliseconds or even smaller. So you need now the CQT high time resolution to pinpoint the exact moment of the crash. And all of this works just amazing. So it is really crucial to understand that how they essentially, if you want, tricked a text model into reading physics data, a gravitational wave signal. No? So you have a step of a translation layer between, if you want, the continuous world of physics and the absolute discrete integer world of a large language model. How they did it? I already told you with a k-mean quantization. Let's have a closer look. Now the problem is the LLMs don't speak float. No, they speak only integer. And Llama 3 is a text model. It has an input layer for the embedding that expects integer token IDs from a fixed vocabulary. So how do we tokenize a gravitational wave in space? The solution is easy. We use k-means here as a dictionary generator. So step A, we extract here the frames or the letters if you want. No? So you take here the CQT spectrogram, which is time times frequency, and they slice it vertically into time steps. That's what we need. No? And each slice is now a vector representation, thereby representing the frequency content of that specific, let's say, millisecond. So like a vector representing, hey, we have high energy at 50 Hz, but low energy at 100 Hz. Great. Then step B. We have to build the codebook. We have to build now our new dictionary. No? It's not anymore words or subtokens. Now it's gravitational wave tokens. So what they do, they take all the vectors from the training data, the real signals, no? And throw them into a pile. And then they run here the k-mean algorithm on this pile because they know those 90 elements are the real thing. No? So k-means now finds generic representative shape of signals. Now, centroid 1 might look like a silence, or a flat noise. Centroid 2 might look like a low rumble. And centroid 3 might look like a high-pitched spike. So you see, we built here our vocabulary, the dictionary. Let's say they choose here k equal, 100, 200 clusters. They now have a vocabulary of 200 unique sound shapes. And the sound is the sound of the gravitational collapse of black holes. And you know now the quantization, so just the translation. No? So for each new incoming signal of a gravitational wave interferometer, they look now at the first time slice and they say, okay, the EI is now looking here and compared with their learned K centroids. And if the first time slide has a real similar signature shape like the K centroids, the AI thinks, it looks almost like the centroid with the name 42. So they replace now that particular time-dependent slice with the integer 42. And this is it. So the result that we achieve is so simple. we have a continuous gravitational wave coming in, and it is now transformed into a sequence of integers. You just have to come up with this brilliant idea. So you see, the model is forced to choose here from a limited menu of standard shapes. This has multiple effects. First, there's a renormalization effect, but also this inherently denoises the input, no? Because unique random noise doesn't fit well with into any standard cluster, so it gets mapped to the nearest genetic noise token, while the strong, coherent, the real signal of the gravitational wave gets mapped to a specific sequence of this is the real signal token. So we achieve exactly what we set out to do, discriminate between noise and signal. What are the conclusions by the authors? The authors conclude, our findings show that LLMs form a viable and efficient alternative to traditional, convolutional neural networks of gravitational wave signal identification. Their ability to handle, LLM's ability to handle complex, non-Gaussian and non-stationary noise, combined with the strong performance in small data sets, parentheses 90 events only, suggests that LLMs may play an important role in future gravitational, space-based wave identification patterns. Yes, we achieved it. Now you know I have my own additional sorts, so let's call it deeper insights. Did you notice that we swapped out a functional from a CNN functional to a transformer functional? Did you notice that this aligned here the mathematical topology of the AI model with the real-world physical topology of the gravitational wave characteristics, thereby turning an intractable big data problem into a simple, trivial, small data problem? So whenever we talk about swapping a probability functional in AI, we are really talking about changing the fundamental rules of data processing within a transformer architecture. The convolutional functional was simple, no? The AI said, hey, I only care about local neighborhoods in my window. It takes a waveform function, it slides a small window over it, it calculates within this window the probability based on only what is inside this tiny window. And the flaw is, this is extreme nearsighted. No? It sees a burst of noise, a glitch, and thinks, hey, this is maybe a real signal, no? Because a CNN can't see the context 2 seconds ago that is outside of its particular window. Complete different performance, complete different methodology to calculate the signal with the attention functional of our transformer. The rule has now changed. The transformer says, hey, I care about the relationship between every part of this signal and every other part in my sentence, in my chunk. And in this chunk, hopefully, is the complete gravitational wave signal. So it takes here the entire waveform functions at once. It calculates the probability, the self-attention, by measuring how much the beginning of the wave agrees, even with up to the end of the wave. So what we achieved is, we can cancel out the glitch. It ignores the glitch, the noise. Why? Because the noise in this transformation is an island. The functional's mathematical rules simply say, hey, if it doesn't connect to the rest of the sequence, the probability that this is the real signal is low. And we achieved exactly what we set out to do. So you see, there is now a way to see this from a pure mathematical lens of functionals, attention functionals and convolutional functionals that provide a much deeper insight into the correct architecture of our AI systems. Okay, this is it. So imagine what we achieved. I mean, the authors achieved it. Tokenizing a gravitational wave signal and swapping the probability functional in our AI systems. So we started here with a gravitational wave data that traveled for, I don't know, maybe millions of years across the universe. We detected. We found a methodology to tokenize here this particular wave data into a tokenized linear sequence input prompt to our LLM. But we had a probability functional swap that we kicked out our convolutional neural network and we inserted our classical transformer architecture. We used a large language model to analyze here the details in the complexity of the interferometric signal of a gravitational wave of, I don't know, two colliding black holes. And we could identify and reconstruct the pure signal waveform as an output. What an amazing journey in astrophysics. I was simply amazed by the beauty of this publication, and I wanted to show you we can use AI in so many intelligent ways for signal conversions I never thought about. But what a beautiful study. Have a look yourself. I say, thank you for watching. I hope you enjoyed it a little bit. Maybe you find it interesting. Maybe you want to subscribe to my channel. Maybe you want to even become a member of my channel and support here this channel. Anyway, I just hope I see you in my next video.